Alright, so this is going to be a real ugly video. We're starting off with, a couple years ago we used the, I'm going to see if I can get this in here right. Yeah. We had the extra methyl group right here. So it was isobutyric acid, but the smell of it was so bad that we eventually, after 10 years of doing it, had to come to a stop and switch it out for the one without the methyl. So this is propanoic acid. So the whole point of we took the acid, we converted it to the acid chloride. That was one reaction. I think it was called reaction 8. Then we took the acid chloride and converted it to the amide. So there's two reactions in a row. So there was a video that had IR, NMR, and even lab discussion-based things. So what we're going to do is compare. In organic chemistry, a lot of times, one of the classic stories is, I found a procedure that used this compound. But what I want to do is use this compound. So in organic chemistry, we would say these two compounds are so close, we call them analogs. So the exact same procedure, a lot of the observations and discussion content should be analogously the same. Certain things are very, very similar, like the IRs, for instance, are often very, very similar. The types of things you're going to circle are going to be the same. The proton and carbons can be a little different just because of the number of hydrogen signals. But the observations and discussion videos are going to stay the same, so you have to learn how to deal with that and analogously make your own. So let's start off. The starting material, the old material, the isobutyric. So I would basically circle the OH stretch of the acid, the carbonyl C double bond O stretch, and for all intents and purposes, that's pretty much the business end of what I would circle in this. The only other thing that somebody could do is circle a little bit of the CH bending stuff, but without a benzene ring in that, there's nothing else that's too indicative. Now, if we jump down to the new one, starting material with no methyl group on it, you see the OH stretch is pretty much the same, the carbonyl is very much the same. So that's the IR of the starting materials. The product was making the acid chloride. So this is the acid chloride of the old days with the methyl group in place. And what you're going to see is the CH sp3 hybridized carbons with H on it stretching. And the carbonyl of an acid chloride often gives two peaks at this higher wavelengths. So you circle this and say it's the CO stretch. Now it turns out that this peak at 1235. Somebody say, oh, it's so big, what is that? Well, we know from this experiment, it's mentioned in the discussion, a lot of students, when you distill it over, we end up having quite a bit of liquid thionyl chloride. So the IR of thionyl chloride pretty much looks like that, and you see one big peak, which is very close to 1235. This one's 1228. When you put a compound in a different matrix with different hydrogen bonding and things like that, it can shift it a little bit. So this student had quite a bit of leftover thionyl chloride mixed in with this one. So that's why that's kind of useful. But let's look at the newer one. And it's the propanoic chloride. The CH sp3 carbons with H's stretching. That one, you can see the overtone of the carbonyl stretch. See how this one has almost like two peaks? So that's what that is again. There's no huge peak for leftover thionyl chloride. So this is the product of the one reaction. So then what we do, back to the old days, we took our acid chloride and we put in ammonia in the IRs and we make this amide. Now, what you're going to see with this one, this is the old compound, you're still going to see a carbonyl right there. The C double bond O stretch of an amide, that's 16 and something. It's kind of broad and that's normal. You're going to see CH stretching, sp3 carbon stretching, and see these two peaks right there. Those are the two types of stretches of the NH2 group, those two. Now let's look at this year's newer analog, which I did not actually write down the structure, so let me get my pen, because it's kind of important if I... Okay, so that's the old compound right there. You're going to have the two methyl groups that are the same, so they're going to make a doublet right there. The hydrogen in the middle talks to these 6, that's a septet, and then the OH is way down here at 12. The newer one you guys are using this year, it's going to look a little different only because you got that ethyl group, which means you expect to see a quartet and a triplet. So you get a quartet, you get a triplet, that's the TMS, and then the OH absorption for NMRs there. Go on to carbon. We had an old carbon right there, and you can see it. You're going to see the characteristic 3 carbon peaks. You should make sense of that. The newer compound is also going to have 3 carbon peaks. You got the ethyl fragment, and you got the carbonyl that's way out here. That's the CH2 group, that's the CH3 group. Then we go on to, that was a starting material. Now we make the acid chloride. So the old days we had something like this. There's no more hydrogen on the acid. That's gone because it's an acid chloride. So all you're going to have is a doublet and a septet for the old one. The new one, no more acid present because you've made the acid chloride. So you're going to see still a quartet and a triplet. CH2 group, CH3. Then we look at the carbon of the acid chloride. The carbonyl stretch down near 177, and then the CH group, and this is the CH3 group. The newer compound, and this was, we took it this year, we didn't have a very concentrated sample, so the peak is very small, but this one says yes, it's the carbonyl carbon. This one, in this compound, this year's, 173, call it 174, and then you're going to see 2 other peaks here. The CH2 group, which is at 40, and then the CH3 group, which is at, let's call it 9. Then we move on to the amide. So the old compound that we made was with the methyl group there. You're going to see a doublet, a septet, and you're going to see, this was chloroform D, but there's a very wide baseline right there, and it does integrate to almost 2. Those are both of the H's on the nitrogen, very broad one. The new compound, and this is the students that we ran this year, and you're going to see there was a little bit of trace leftover aromatic stuff, probably dirty in the NMR tube, but this compound is going to have a quartet and a triplet, so you can see that right here, quartet, triplet. And then right here, you can kind of make it out. There's almost like 2 bumps. Those are the 2 separate H's on the NH2 group. And that does happen. Sometimes you see 1 blob, sometimes you see the 2 of them kind of separate, each worth 1 hydrogen. So that's the proton. And now we go to the carbon. In the old compound, this particular one has chloroform D at 77. We mixed it with DMSO to get it, so that's a DMSO solvent peak. The carbons is the methyl and then the CH group, methyl, CH group. And way over here at 177 is the carbonyl carbon. That was the old compound. The new one that we made, minus that methyl group, you're going to see 3 carbon signals. One of them is at 177, and then the other 2 are at 28. That's the CH2 group. The CH3 group is 10.1. So folks, you can basically compare these. I've copied these so you have copies of them. So you can take a look, and then you can basically use the videos for the discussion of both of those reactions, the acid chloride and the amide. And a lot of the observations and results and discussion content is very much similar to the reactions we're doing with the newer compound.